There is a letter that Albert Einstein wrote in March of 1955, just weeks before his own death, to the family of his closest friend, Michel Besso, who had just died. In that letter, Einstein offered consolation by writing that Besso had departed from this strange world a little ahead of him, and then he added something that has stayed with physicists and philosophers ever since. He wrote that it signifies nothing, because for us who believe in physics, he said, the distinction between past, present, and future is only a stubbornly persistent illusion. A stubbornly persistent illusion. Those words did not come from a mystic. They did not come from a poet or a philosopher operating at the edges of respectability. They came from the physicist who gave us special relativity and general relativity, who unified space and time into a single four-dimensional structure, who more than any other person in the 20th century transformed our understanding of the most basic features of reality. And he was saying, in what amounts to one of the most profound scientific statements ever put in a private letter, that time, the past, the present, the future, that river of moments you feel moving through you right now as you take in these words is an illusion. And I want to take that seriously. Not as a figure of speech, not as the kind of consoling sentiment a brilliant but grieving man writes to comfort a bereaved family. I want to take it seriously as a scientific claim, and I want to follow it wherever it actually leads. Because here is what I find so extraordinary about this question. The deeper you go into it, the more carefully you examine what physics says, what thermodynamics says, what quantum gravity says, what neuroscience says, the more complicated, the more unsettled, and in many ways, the more genuinely strange the answer becomes. Is time an illusion? I want to begin by pointing out that this question is actually several distinct questions tangled into one. And the different questions have different answers, and the different answers don't all point in the same direction. So let me try to separate them. There's the question of whether time as a dimension, as a coordinate in the four-dimensional structure of space-time is real. There's the question of whether the flow of time, the sense of movement from past through present to future, is a fundamental feature of the external universe or something generated by our situation within it. There's the question of whether the present moment, this specific privilege now, is objectively real or observer-dependent. There's the question of whether the distinction between past and future, the arrow of time, is fundamental to the laws of physics or emergent from them. And there's the question of whether our experience of time, the vivid, immediate, felt sense of living in a moment, accurately reflects something about the external world or is a construction of the brain. These are 5 different questions, and I want to work through all of them, because I think the full picture that emerges is one of the most extraordinary things that careful thinking about time has ever produced. Let me start with physics, and let me start with Newton, because Newton is where our modern scientific picture of time begins, and because Newton's picture is still, in many ways, the one that most people carry around implicitly even today. For Newton, time was absolute and universal. He wrote this down explicitly at the very beginning of his Principia Mathematica in 1687. Absolute, true, and mathematical time, he wrote, of itself and from its own nature, flows equably without relation to anything external. Time ticks. It ticks the same way everywhere. It ticks the same way for everyone. There is one universal clock, and every event in the universe can be assigned a precise moment on that clock, a definite time at which it occurred, the same for all observers. In Newton's universe, if you and I are standing on opposite sides of the galaxy, and I ask what time it is right now, there is a single correct answer that applies to both of us simultaneously. Now is now, everywhere, always. This picture is intuitive. It fits everything we experience in daily life. It produced physics so accurate and so powerful that it got us to the moon and back, that it let us predict the paths of planets and comets and satellites with extraordinary precision, Newton's mechanics worked. It worked brilliantly for 2 centuries. And then in 1905, it turned out to be wrong. What happened was light. In the late 19th century, experimental results and theoretical puzzles were accumulating around the behavior of light that simply could not be reconciled with Newton's picture. The most important of these was the constancy of the speed of light. Every experiment conducted in every possible way found the same thing. Light travels at the same speed relative to any observer, regardless of how fast that observer is moving. If you're racing toward a light source, the light comes at you at exactly the same speed as if you were standing still. If you're racing away, same thing. The speed of light appears to be an absolute constant, observer-independent, frame-independent, apparently inviolable. This is not what Newton's framework predicts. In Newton's world, if I'm running toward you at 10 miles per hour and you throw a ball at me at 30 miles per hour, I see the ball coming at 40 miles per hour. Speeds add. But light doesn't add. Light stubbornly arrives at the same speed regardless of relative motion. Something was wrong, or at least incomplete, in Newton's picture. Einstein's response to this puzzle in his 1905 paper on special relativity was radical in its simplicity. Take the constancy of the speed of light as an axiom, he said. Accept it as an absolute law of nature, and then ask what else must be true for this to be consistent. And the answer that fell out of the mathematics was this: Newton's absolute time had to go. Time is not universal. Time is not absolute. Time is relative. Different observers in different states of motion experience time at genuinely different rates. The faster you move through space, the more slowly your time passes relative to a stationary observer. This is time dilation, and it is not a theoretical curiosity or a philosophical speculation. It is a measured, verified, daily operational fact. The clocks aboard GPS satellites run at different rates than clocks on the ground, faster because of altitude, slower because of speed, and the entire GPS system depends on correcting for this. The atomic clocks we use to define time itself show this effect. Muons created by cosmic rays at the top of the atmosphere survive long enough to reach detectors on the ground only because their internal time runs slow relative to us. Time dilation is as real as anything in physics. But there is something even more profound than time dilation lurking in special relativity, and it is the relativity of simultaneity. It is the fact that not only do different observers experience different rates of time passage, but they also disagree about which events are simultaneous. What one observer calls 2 events happening at the same time, another observer in a different state of motion will say happen at different times, one before the other. And both observers are right in their own reference frames. There is no privileged frame. There is no frame that can be said to tell us the objectively correct answer about whether 2 events are simultaneous. This is one of the most profound and most underappreciated consequences of relativity. Think about what it means. The present moment right now is, by definition, the collection of all events that are simultaneous with this moment. But if different observers have different equally valid definitions of simultaneous, then different observers have different equally valid present moments. Your now is not the same as my now if we're in different states of motion. There is no single, universal, objective now that applies to everyone, everywhere. And here is the consequence of this that I find most striking. Consider someone in a galaxy 4 billion light years away, walking at a casual pace in your general direction, not in a rocket, just walking. Due to the geometry of space-time and the relativity of simultaneity, this person's present moment, the slice of space-time they would call now, includes events in your world that you would call 400 years in the past. And if they turn around and walk away, there now shifts to include events 400 years in your future. A slight change in the motion of a distant observer radically changes which events on Earth belong to their present, which means your past and your future must both exist, must both be real, because they are, respectively, someone's present right now. This is the block universe, sometimes called eternalism by philosophers. The idea that the four-dimensional structure of space-time, past, present, and future exists all at once as one static, unchanging block. There is no objective flow moving through it. There is no universal now sweeping from past to future. There are just events embedded in a four-dimensional geometry and different observers taking different three-dimensional cross-sections of that geometry, each calling their cross-section the present. The mathematician Hermann Minkowski, who formalized this geometrical picture in 1908, said it beautifully in a famous lecture, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. It is space-time, not space, not time separately, that is real. And in that space-time, all events are embedded with equal ontological status." This is what Einstein meant in his letter. The distinction between past, present, and future is only a stubbornly persistent illusion, not because time doesn't exist, but because the flowing, privileged, now we experience doesn't correspond to anything in the physics. The block universe has no preferred moment. It has no moving spotlight sweeping from past to future. It just is. Now, I want to acknowledge something important here, because this is not a view held by all physicists. There is a serious minority position defended by serious physicists that pushes back on the block universe. The physicist Lee Smolin, one of the founders of loop quantum gravity and a faculty member of the Perimeter Institute for Theoretical Physics, has written a book arguing exactly the opposite of Einstein, that time is real, that the present is privileged, and that the block universe is a mistake. Smolin's argument, developed in his book Time Reborn, is roughly this. The block universe is derived from our mathematical models of physics, which are themselves timeless representations constructed from outside the universe, viewing all moments simultaneously. But no physicist, no observer is outside the universe. Every observer is inside it, embedded in it, experiencing one moment after another. And Smolin argues that taking this inside view seriously, rather than the God's eye view of the mathematical model, reveals that time is more fundamental than our equations suggest, not less. Smolin goes further. He argues that the laws of physics themselves are not eternal, fixed, Platonic truths written into the block outside of time. They evolve, they change. And a universe with evolving laws is a universe in which time is real in a way the block universe cannot accommodate. This is a genuinely minority view, and most of Smolin's colleagues remain unconvinced. But the fact that someone as careful and rigorous as Smolin makes this argument is worth pausing on. It tells you that the block universe, while the dominant view, is not settled beyond question. Let me now move to quantum gravity, because this is where the story gets even more interesting and more strange. In ordinary quantum mechanics, the quantum mechanics of particles and fields, of electrons and photons, time appears as a background parameter. It's just there. It ticks in the background, providing the parameter against which quantum states evolve. There's nothing quantum mechanical about time itself in ordinary quantum mechanics. It's as absolute and universal in this limited sense as Newton ever imagined. But when you try to combine quantum mechanics with general relativity, when you try to write a quantum theory of gravity, a quantum theory of space-time itself, something extraordinary and deeply disconcerting happens. Time disappears. This is not a metaphor. This is a technical, mathematical fact about the equation that physicists in the 1960s wrote down when they tried to apply quantum mechanics to the gravitational field. The equation is called the Wheeler-DeWitt equation, named after John Wheeler and Bryce DeWitt, who derived it in 1967. The Wheeler-DeWitt equation is the closest thing we have to an equation for the quantum state of the entire universe. It describes the wave function of the universe, the complete quantum description of everything, and it contains no time variable, not a hidden time variable, not a time variable we haven't found yet, no time at all. The equation is static. When you ask the equation how the universe evolves, it says it doesn't. The quantum state of the universe, at the most fundamental level of description we currently have, is timeless. It just is. There is no before, no after, no sequence, just the wave function, eternal and unchanging. This is what physicists call the problem of time in quantum gravity. It's one of the deepest unresolved problems in all of theoretical physics, and it cuts right to the heart of the question we're asking. If the fundamental equation describing the quantum state of the universe has no time in it, what does that tell us about time itself? One response is to say it tells us time is not fundamental, it's emergent. It arises from the quantum state in some coarse-grained, approximate thermodynamic way that we don't yet fully understand, but that makes time appear to observers inside the universe, even though the universe as a whole, at the most fundamental level, is timeless. This is roughly the view of Carlo Rovelli, one of the most creative and prolific physicists currently working on quantum gravity, who has written about these ideas in his beautiful book, The Order of Time. Another response, proposed by Don Page and William Wooters in 1983 and developed more rigorously since, is that time within the universe is an internal relationship, a correlation between a subsystem called a clock and everything else. You, embedded within the universe, experience time because the quantum system you call a clock, whether that's a physical clock, the light from the sun, the oscillations of atoms in your brain, is entangled with the rest of the universe. When you read the clock, the entanglement projects the rest of the universe into its corresponding state at that time. From outside the universe, everything is timeless. From inside, the correlations create the experience of evolution, of change, of time. This is a profound idea, and it's been given experimental support. In 2013, physicists at the Istituto Nazionale di Ricerca Metrologica in Italy performed an experiment using entangled photons that provided direct evidence for the Page-Wooters mechanism, showing that time, as experienced by an observer inside a quantum system, arises from quantum entanglement even when there is no external clock. Time, in this view, is not a feature of the universe. It's a feature of being inside the universe, entangled with it, reading its internal correlations. Now, let me shift direction completely and talk about thermodynamics, because I think thermodynamics is where some of the most important and most underappreciated physics of time lives. Here is a fundamental fact about the equations of physics that I want you to hold in your mind. With one exception, every fundamental equation of physics is time symmetric. Newton's laws, Maxwell's equations of electromagnetism, Einstein's general relativity, Schrödinger's equation of quantum mechanics, Dirac's equation, the standard model of particle physics. Every one of these equations works exactly the same way, whether you run time forward or backward. If you film a billiard ball collision and play the film in reverse, it looks like a perfectly valid billiard ball collision. If you film two electrons scattering off each other and play the film in reverse, you get a valid electron scattering event. The fundamental laws are time symmetric. They have no preferred direction in time. They do not distinguish between past and future. There is one exception, just one. In all of fundamental physics, there is one equation, one law that knows the difference between past and future. And it's the second law of thermodynamics. Entropy never decreases. Entropy is, roughly speaking, a measure of the number of microscopic configurations that are consistent with a given macroscopic state. A glass of warm water with cream thoroughly mixed in is a high entropy state. There are an enormous number of microscopic arrangements of the water and cream molecules that all look at the macroscopic level like warm, mixed liquid. A glass of cold coffee with the cream still in a distinct layer is a lower entropy state. There are fewer microscopic arrangements consistent with that clearly unmixed appearance. The second law says that closed systems evolve from lower entropy states to higher entropy states. The unmixed layer mixes, the hot tea cools, the organized structure disperses. And it never spontaneously reverses. You have never seen a cup of coffee spontaneously unmix itself with the cream rising back into a perfect unmixed layer. The second law forbids it, but here is the crucial point. The second law is not a fundamental law in the same sense as Newton's laws or Schrödinger's equation. It is statistical. It emerges from the underlying time-symmetric microscopic laws, combined with the fact that high entropy states are overwhelmingly more probable than low entropy states. There is nothing in the microscopic laws that prevents the cream from unmixing. It's just that the number of molecular configurations that would produce spontaneous unmixing is vanishingly small compared to the number that produce further mixing. It essentially never happens by chance. But it's not forbidden by the fundamental laws. It's just absurdly, incalculably improbable. So the direction of time, the past to future arrow, the direction of increasing entropy is not built into the fundamental laws of physics. It's built into the statistics, into the probability landscape, and ultimately into the fact that the universe started in an extraordinarily low entropy state. That last point is crucial and remarkable. Why does the arrow of time point in a consistent direction across the universe? Why does entropy increase everywhere for everyone in the same direction? The answer is that the entire observable universe emerged from the Big Bang in a state of extraordinarily low entropy, almost incomprehensibly low entropy, and it has been climbing the entropy ladder ever since. Every irreversible process in the universe, every mixing, every cooling, every decay, every death is entropy increasing along this arrow that originated 13.8 billion years ago in the first fraction of a second after the Big Bang. And here is where Ravelli's argument becomes most interesting. He points out that our concepts of past and future memory, causality, the very distinction between what has happened and what might happen, all depend on this entropy gradient. Memory exists because the past leaves low entropy traces that the present can read. A footprint in sand is a low entropy configuration of sand grains that encodes information about the foot that made it. A photograph is a low entropy arrangement of photons and pixels that encodes information about the scene it captured. These traces exist because entropy was lower in the past. If entropy were not lower in the past, if the universe were in equilibrium with no entropy gradient, there would be no traces of the past. Memory would be impossible. Causality would have no direction. The distinction between past and future would vanish. But here's the most startling part of Ravelli's argument. He says that entropy is not an objective property of the physical world. It is, in a deep sense, relative to the observer. To the coarse graining you apply, entropy is high when there are many microscopic states consistent with the macroscopic description you're using. But what counts as macroscopic? What counts as a description? This depends on which variables you can observe, which degrees of freedom you have access to. A Maxwell's demon, a hypothetical entity with perfect information about every molecule, would see no entropy at all. Everything would be perfectly specified. No statistical uncertainty, no entropy, no arrow of time. Time, in this picture, is not a property of the universe. It's a property of the relationship between the observer and the universe. It emerges from the fact that we are macroscopic creatures with limited information, unable to track the full microscopic state of the world. Given that limitation, entropy is real, the arrow is real, and time, the distinction between past and future, is real. But it's real in the way temperature is real. Temperature is a genuine, measurable property of a gas. But it makes no sense for a single molecule. It arises from the collective behavior of many molecules, from a coarse-grained description. Similarly, time arises from a coarse-grained description of a universe evolving away from a low entropy initial state. And this connects to the most radical version of the time as emergent view, put forward by the British physicist Julian Barbour in his book, The End of Time. Barbour argues that time doesn't exist at all, not as a fundamental feature, not even as a useful approximation. What exists, Barbour says, are configurations, instantaneous, timeless snapshots of the arrangement of everything in the universe. And what we experience as time is the fact that these configurations contain records of other configurations. The memory in your brain right now, your sense of having lived through a sequence of moments, is a feature of your current configuration, a low entropy trace encoded in your neurons. And because configurations with records of other configurations are vastly more probable than configurations without such records, almost every configuration that exists will appear to any observer embedded in it. To be embedded in a sequence will appear to be a moment in time. The flow of time is not real. The configurations are real. The apparent flow is what you necessarily experience when you're a record-containing configuration in a universe of such configurations. Barbour's view is the most radical and in some ways the most logically consistent, but it's also the most counterintuitive. And it's not clear what experimental difference it would make compared to the block universe view. If you're inside one of Barbour's timeless configurations, your experience would be indistinguishable from being inside a block universe. Both pictures predict the same observations. Now I want to turn to something even more personal. I want to turn to you. I want to talk about what your brain is actually doing when it generates your experience of time. Because this is where the story becomes, in many ways, most intimate and most strange. Your experience of time right now, the sense that you are in a flowing present moment, that the past is behind you and the future is ahead, that experience is generated by your brain. It is not a direct recording of external physical time. It is a construction, a model, an interpretation of signals that arrive in your nervous system with different delays from different sensory channels, processed by different neural pathways, and integrated into a seamless, coherent experience of now. And this construction is, in measurable, documented, experimental ways, an imperfect representation of physical reality. Let me give you some examples. Your different senses have different processing delays. Light signals from your retina take something like 80 to 100 milliseconds to reach conscious perception. Auditory signals are processed faster. Tactile signals travel up your spinal cord at speeds that depend on the length of the neural pathway. The same event registered by your toe arrives at your brain significantly later than the same event registered by your fingertip. Yet your experience of the world is synchronous. When you watch someone clap their hands nearby, you experience the sight and the sound as simultaneous, even though physically the sound arrives slightly later than the light. and neurologically different processing times are involved. For each, your brain is actively synchronizing these asynchronous inputs. It holds back its presentation of experience, running on what David Eagleman at Stanford has called a short time delay. Like a live television broadcast that's actually on a brief delay for editing purposes, just long enough to reconcile the different arrival times and construct a coherent, synchronized experience. The present moment you experience is not the immediate, unedited feed from your senses. It is a post-produced version assembled slightly after the fact. And your brain can reassign the order of events in time in ways that seem deeply paradoxical. There is a class of experiments studied extensively in the neuroscience of time perception called the temporal order judgment recalibration experiment. In these experiments, participants press a button and see a flash on a screen. If you introduce a delay of around 100 to 200 milliseconds between the button press and the flash, participants quickly recalibrate. Their brains learn to expect the delay, and they begin to perceive the flash as simultaneous with the button press, even though it comes slightly after. So far, so sensible. The brain adapts to consistent delays. But here's where it gets strange. If you then suddenly remove the delay and make the flash truly simultaneous with the button press, participants perceive the flash as coming before the button press. They experience cause and effect in reverse order. The flash appears to precede the action that caused it. The brain, having calibrated to a world where the flash is delayed, overshoots when the delay disappears, and for a brief moment, subjective time runs backward relative to objective physical time. This is not a minor measurement artifact. This is your brain doing something in your experience of time that doesn't happen in physical time. Your brain is constructing a temporal narrative, assigning events to temporal positions, and that narrative can run backward relative to physical reality. The order of events in your experience is not a passive recording of the order of events in the world. It's an active construction that can be manipulated, recalibrated, and sometimes reversed. And the now that you feel living in the vivid present moment is not a point, it's a window. Psychologists and neuroscientists have studied what they call the specious present, the temporal window within which events are experienced as simultaneous as part of the same now. This window is not instantaneous. It spans roughly 2 to 3 seconds of physical time. Events that happen within 2 to 3 seconds of each other are integrated by your brain into a single unified present experience. Events outside that window are experienced as sequential, as past or future relative to now. Think about what that means. The thin, needle-like present moment of philosophical intuition, the razor edge between past and future, is not what you actually experience. You experience a smeared out, brain-constructed window, an integration over a significant chunk of physical time. Your now is not a moment. It's an editorial summary of the last 2 to 3 seconds presented as a single, coherent present. And your memory of time, your sense of having lived through a past, is equally constructed and equally imperfect. Memory is not a recording. It's a reconstruction. Every time you remember something, you are rebuilding it, reassembling it from stored fragments, and the reconstruction can introduce changes, add false details, shift the temporal sequence of events. The past that you remember is not simply the past that happened. It's a narrative maintained by a brain that is constantly revising its own history. So now let me try to bring all of this together, because I've presented you with a lot of different pieces, from special relativity to quantum gravity to thermodynamics to neuroscience, and I want to see what picture they collectively paint. Here is what I think the evidence tells us, as clearly and honestly as I can state it. The temporal dimension is real. Space-time is a genuine four-dimensional structure. Events are embedded in it. Causal relationships connect them. This is physics, and it is as well established as anything in science. The absolute universal present moment is not real. It is observer dependent. Different observers in different states of motion have different, equally valid present moments. There is no universal now. Einstein showed us this in 1905, and a century of experiments has confirmed it. If you think of yourself as living in a single, special now that is objectively privileged over all other times, that thought is mistaken. It is a parochial fiction generated by the fact that you are a slow-moving, large-scale observer whose differences from other reference frames are so tiny that the relativity of simultaneity is completely imperceptible in daily life. But it's not real. The flow of time, the sense of movement from past to present to future, is not a fundamental feature of the external universe. The fundamental equations of physics do not describe a flowing time. The block universe does not flow. The flow is generated by our thermodynamic situation, by the entropy gradient we are embedded in, by our coarse-grained macroscopic relationship to a world whose past was extraordinarily low entropy. If we had complete information about every microscopic degree of freedom in the universe, the distinction between past and future would dissolve. The flow is real for us, but it's not written into the deepest physics. The arrow of time, the distinction between past and future, is real but emergent. It emerges from entropy, which emerges from the statistical behavior of many particles, which traces back to the extraordinarily low entropy of the Big Bang. The arrow is consistent and reliable. It makes memory possible, causality meaningful, life livable, but it is not fundamental. It is not written into the microscopic laws of nature. It is a consequence of our particular cosmic history. At the level of quantum gravity, at the deepest level of description we currently have, time appears to be absent. The Wheeler-DeWitt equation has no time. Whether this means time is truly emergent from something more fundamental, or whether it means our current approach to quantum gravity is missing something, is a genuinely open question. But the fact that our most complete attempt to describe the quantum state of the universe produces an equation with no time in it is, at minimum, an extraordinary and deeply suggestive fact. And the experience of time, your immediate, vivid, moment-to-moment sense of living in the present, of time flowing, of the past being behind you and the future ahead, that is a genuine experience. But it is a construction, a model assembled by your brain from asynchronous sensory signals, held on a brief delay for editing, integrated over a 2 to 3 second window, and capable of assigning events to temporal positions that don't always match physical reality. The experience is real in the sense that it is genuinely happening, but it is not a transparent window onto the physics. So is time an illusion? It depends on what you mean. If you mean, is the temporal dimension a fiction? Does time not exist at all? The answer is no. Time exists. The temporal structure of space-time is as real as the spatial structure. Events have temporal relationships. Causality is real. Duration is real. If you mean, is the flowing, present moment centered, past is gone, future is not yet arrived experience of time an accurate description of what the universe is fundamentally doing, then the answer is much closer to yes. The flowing present is not a fundamental feature of the universe. It's a feature of our situation within the universe, of our thermodynamic situation, our cognitive architecture, our epistemic limitations, and our specific location in a space-time block that has no objectively privileged now. The physicist John Wheeler, who spent a lifetime thinking about time and quantum mechanics and the nature of reality, said something I love. Time is what prevents everything from happening at once. I love that formulation because it captures something true and important. Time is the structure that orders events, that separates causes from effects, that makes the universe intelligible rather than a single undifferentiated explosion. In that sense, as a structural feature of the space-time block, time is absolutely real. But the specific story we tell ourselves about time, the river flowing, the present uniquely real, the past genuinely gone, and the future genuinely not yet arrived, the clock ticking absolutely and universally, that story, in several of its most important features, is wrong, or at least profoundly incomplete. And the way it's wrong is not random or arbitrary. It's wrong in ways that physics and thermodynamics and neuroscience can precisely characterize and explain. There's one more thing I want to say, and it connects back to Einstein's letter. Einstein wrote to console a grieving family. He wrote that for those who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. And he said this in the context of telling them that Michel Besso's departure from this strange world signifies nothing. Because in the block universe, Besso's moments of existence are not gone, they are not destroyed. The conversations he had, the thoughts he thought, the friendships he maintained, the decades he spent as Einstein's closest intellectual companion, those moments are embedded in the block. They exist in the four-dimensional structure of space-time with the same ontological steps.